I wanted to try something different and pick a different topic. My original topic, I mentioned to Bob, he said, how about this topic? Oh yeah, that's a little better, probably not great. It's only related to calculators in the sense that I use the calculator a lot for what I'm going to do. So my question to you, how many of you do not own, have, or use a digital multimeter?
Do or do not?
Oh, okay, I was right.
I'm looking for one though, if that's...
Okay, excellent. So most of you at least know what a digital multimeter is, okay? And as you can see up on the screen here, I have probably close to 200 digital multimeters, all right? I've been collecting them for 40 years. So I have some really old ones. And so these are the ones I'm going to compare each other and talk about. And I'm not going to go into the nitty-gritty of every little specification. That's not the point. But one of my objectives was to show you, I guess I'll use the word unusual applications of the digital multimeter. Things that you wouldn't think about using the multimeter for. Now the first one here is, first of all, these, this by the way is the cover page of the paper that's on your drive. And I really wanted to have more information in there, and I ran out of time, so it's only 103 pages long.
Is that like Mark Twain? He would have written a shorter paper, but he didn't have the time.
Yeah, exactly. So this is the cover page, and I want to mention the machines as we go. Most of these are handheld. And like a friend of mine who told me about the machine that I got excited about in 2017, he says, hey, I found this unusual Chinese-made, the name of the company is ANENG. I don't know how you pronounce that, ANENG. Aneng, whatever, it's Chinese, all right? So, and that was the model at the time in 2017 was the ANG 8008. And what was unusual about that meter is it was a true 4-digit machine, instrument. Normally, the average meter that you have is something like this. You can buy this at Harbor Freight. And this model is amazing. It's like the HP12C. It just has never gone away, and it's the longest one available continuous machine. This, for a readily available multimeter, digital multimeter, this is the 7th function El Cheapo bottom end machine. And Harbor Freight had coupons that if you brought the coupon in the machine into the store, they gave you one free. So I have 30 of those.
I have seen them.
Well, they're free. I mean, this is over a 10-year period, of course. You know,
Real money for one.
today with all the inflation, what have you, this is $7.95.
Oh, really? That much?
But this is 3.5 digits. Now, what does that mean? In the early days of multimeters, the screens were an expensive part of the meter. So you would have, you know, here's 9.98, but there's a digit over here, a single 1. So they could give you more resolution by giving you what they called a half digit. So this could read 1998, and you have a 4-digit display, but it's only a 3.5 digit of resolution. And I don't have a copy. We'll see how it goes here. So the first one here is a pretty large machine. This is the model 870. This is a, if they were talking normal market terms, a 4.5 digit machine, instrument. But that's not the best way you should look at it. The best way to look at it is how many counts. That's 19,999 counts. The 8009 is 9999, that's almost 10,000 counts. 9,999 counts. And this one over here is a Zotek model ZT111. That's exactly the same as this one. It's just marketed under a different name, 999 counts. And this one over here, well, this is the only, this is a new model, because when you look at a digital multimeter, you have this rotary switch. This has no switch. And that rotary switch is mechanically unreliable. You use it for 10 years, and so this machine has the functions and specifications of this machine, but no rotary switch, and it's half the price. So you're talking about this one on the order of $12 here, and that's a 9,999 count machine. And then the whole front of it is no switch, but it's just display, and you have to get used to using it. Plus the fact it is also an auto mode. Say, if you want to measure DC volts, you put it on DC volts, and it automatically selects the range and gives you the value. Now, this is the only fluke I own. I know I'm jealous of Eric. He's got a real fluke. And one of these days, I'll buy one 87V, what is it? Okay.
If it works, it's a fluke.
No. All right, this fluke, they were on sale. I bought 2 of those. I have 2 of these. I got 30 or 40 of these. And this one over here is an analog multimeter. And of course, what I've done here for this overview is to use a voltage, I'll use the word standard, but probably should be called a voltage reference. But this reference is, here's the one here. And this reference, you get the paperwork, and it's traceable to NIST, and it's 10.0000 volts. So if there's anything in your world that you want to consider this is the standard, it could be this. And so I consider this is real, and as these instruments read here, I have the error. Error minus 0.2%. Here's my favorite machine, 8009, error 0%. For those like me who like to do measurements and when it should be 13.123 volts, and 13.123 volts. That's nirvana. It's like drinking a beer, right? So here's an analog for comparison. Now, I want to be able to read these, and analog meters are always difficult to read. And you can see the pointer here. It's 10 volts, and it's a 10 volt range. You know, I'm getting really the full thing, but I enlarge that here, and then that enlargement, because here's your 10 volt thing, and this is 0.2 volts less, so this is 0.2 volts here. And then I print this on an 8.5 by 11 sheet of paper. Then I take a vernier caliper, and I measure this, and I measure this, and I do the proportion, and I get 10.16 volts. All right? Now, that's the overview, and my problem is my best demonstration to show you, I left the parts at home. Okay, and that part was a light emitting diode. Now, I was going to ask some of our more electrically oriented, maybe Jim and Eric and so forth, I was going to ask them some challenging questions, and I was going to give them a reward, and that reward is a is this little it's described that as an LED PCB USB. And of course the USB is that this can plug into any USB source, and it's got 3 LEDs in series, and it's a standard LED. That's all I've got to use as an LED, but I think it's going to work. We're going to try that. And so I have, let's see, now I'm done with this.
There you go.
Okay, so this is the short, very few slides of the PowerPoint presentation. And then after I gave it to Eric and I slept a day and a half, get caught up, Eric can relate to that, I added some more stuff to it. So here it is, the 6 DMMs, and I kind of went through this information here. Okay, here's the paper. It's 103 pages. Now what I wanted to do was to make this a reference for anybody who's going to use a digital multimeter. So you say, how do I measure 30,000 volts? You can go to a portion of the paper. How do I measure one micro ohm? For example, I'm going to measure this. Here's a piece of copper wire. I'm going to measure this, and by knowing the resistance, I go to a table, I can tell you what gauge this wire is. You know, the unusual things. Temperature coefficient, so forth. All right, now, various techniques engage. So, because the topic is so big, I want to cover things that be more interesting to you. So let's make this a bi-directional activity here. And the web camera, yeah, thank David for the web camera, by the way. Next page. What I did was to write a rather 4 or 5 pages for the actual paper, and then I put things in appendices because I've been writing about this for 20 years. So I have, I don't know, 50 different articles. And I call them writing projects. That's what I do when I'm retired. I wake up one day and say, you know, an LED is a device, it's really a transducer, right? That means that if I put current into the LED, it gives light. But what if I put light into the LED? Does it give current?
Yes.
Ooh, what?
I said yes.
I said no.
Excellent, excellent. Okay, we're going to find out. So it's you know, it's a give and take. So anyway, what I did was to add these appendices. Now the appendices were written in the same format. So the appendices is an article with its, this is an article with appendices, and because this is an appendix and an appendix, it's a little confusion when you see the thing itself. So what I did is I put an HHC in front of the appendix for the HHC presentation. So if you see an appendix C without an H in there, that's part of an appendix of this, okay? So what the first one is characterizing CCCs, cheap Chinese copies, and that is 7 pages long. It starts on page 17 of this document. And I thought I had given that as a presentation at HHC. Turns out I hadn't. B was 7 accuracy specification methods compared side by side. And includes, here's calculated really, 30 plus HP48 programs. I think I have it later. We'll get back to this. This is very handy because it has vertical columns of parts per million, percentage. One column is, you know, a half-digit calculator, you know, 1 digit to 1.5 digits, 3.5 digits, and then you can say, well, a 3.5 digit calculator is only 1999 counts, and a 4-digit calculator is 9999 counts. Now, what would be the difference between a true 4-digit multimeter and a 3.5 digit multimeter. How would you compare that? I mean, why would you need a 999 count multimeter versus a 1999 count? Any answers? No, okay.
You're gonna tell us.
The counts are the resolution, not the accuracy. Both meters could have the same accuracy, but one meter is showing you more digits. Why do you want more digits? Because if it's changing, you better know the direction and the amount. Appendix C is a writing project comparing the Fluke, in Eric's honor, and the ANG model 8009. That's 21 pages. Because I have the standards that I invested in, I can take a multimeter and say, well, here's a capacitance range, here's a very known accurate capacitor, which is very hard to get, and I can determine whether it passes or fails in terms of its specifications. I think the Fluke 101 had 3 fails. Now, one particular measurement that these meters make is called ACRMS voltage, and it's not uncommon for a meter not to pass the test. I won't get into all the technical details why. And down here, measured in 8009 specifications. This is useful for just the methods described that may be used for any multimeter. And the only reason I can explain that they don't give you the specifications is that the other competitions don't do it, so why should I do it, you know? They're only forced to do it unless somebody all of a sudden says, I'm going to give you all the specifications. The accuracy specifications they will give you, but will they tell you what the input resistance is? Not necessarily. Will they tell you what the burden is when they're measuring current? They don't give that. So what I did is I took, statistically just one sample, and I measured all the missing specifications in that article. Appendix E is checking the AN870 DM with the DMM check plus. Now that's another standard here, which if you're a serious multimeter, digital multimeter user, you want to have this. Now this has got 4, you get a certification sheet with this. So while they'll tell you this, I have a resistance of 1K, 10K, 100K, 100 ohms. Okay, you have those values that you can check your multimeter against.
Oh, okay.
And this is also NIST traceable. So you can check inductors, capacitors, resistors. You have an AC/DC voltage standard. You have a 1 milliamp current standard, and you have an option that from the AC measurements that you can select a second frequency. I think its standard is 100 hertz, and I usually get 1,000 cycles or 1 kilohertz. And so you can check all of your functions with this. My argument, only because I'm a writer using the multimeter in my writings, I'm trying to achieve an accuracy of 1%. That's my goal. Now, most of any of the ones on the cover, a DC voltage will be the most sensitive, the most accurate. That's 0.5%, plus or minus 3 counts. I'll get into that plus or minus because it's digital. There's 2 values needed to describe the accuracy. This device, now, Eric, in the old days, and maybe he's coming around, he bought 5 of them. Well, why did you buy 5?
To give some as gifts. I gave one at the door prize table last year.
So you're a kind person, and yeah. So he gave one last year on the price table. Who won that? Is it the person who won that here? I guess not. You can look at my report, the person's name who won one. And he's using one, so he's got 3 more. You know, see him at the break and, you know, talk him up a little bit and maybe he'll give you one. This thing, so rather than buy a $300 quality Fluke, and I'm not knocking Fluke, they're rugged, they will hold their accuracy over years and years of use. They're, well, normally compared to everything else, they're well supported, but in my accuracy, my evaluation here, you see, Fluke also makes some of their instruments in China. And some of the die-hard Fluke users, like the die-hard calculator users, they're saying, oh, well, made in China, you know, their quality is declining and all that. So rather than spend $300 on a Fluke, I will take $75 and buy 3 of the AN meters. Buy 3 of these, all right? And buy 1 of these. This is $225. NIST check this plus reference. And this design, now I've been following the company, the original company was called voltagestandard.com. Nice website name, right? And that guy, it's a single person, who started that business, had a PPC true philosophy. In other words, I'm going to sell you this product, I'm going to give you all the schematics, I'm going to give you everything that's known about it, and you can go and do it yourself. Here's all the details, or you can buy it from me. Totally transparent and really enthusiastic.
You used about 30 minutes, so I want to make sure you get to your demo.
Oh, okay. Let me go through this. F is the low-end digital multiplier is the SO2. That's some information about that. And G is a short, very low resistance and capacitance test leads. And the 10-volt descriptive text from voltagestandard.com website. Okay, well, next. Digital multimeter techniques. Measuring milliohm resistances. Determining stranded wire AWG number. Does everybody know what the Americans wire gauge standard? That's a standard that the US uses. If you do some wiring in your house, you're going to use 14 gauge. You can use a 12 gauge for your normal house wiring. And you can buy it as solid or stranded. And of course, as a stranded, it's going to be different from the solid. So the stranded equivalent of the solid has an AWG number. And I wanted to use this one. Here's some stranded, but I didn't have time. I really needed to dip this into my solder pot so that this is a guaranteed connection to all 7 strands. And same way over here. And then, okay, here's the stranded number that I bought at Home Depot. What is the gauge number? Because, you know, measuring this is not it's tough because you're talking milliohms, you know. All right, quickly measure many devices, sorting resistors. Well, here's my little project. I have an internet friend who lives in Boise, Idaho, and we started, I won't go into how we met, but we both had same interests. He was an ex-HP employee. He does have an HP calculator, not an enthusiast, and so forth. And so, and I always send him copies of my articles, and he stacks them up on his computer. And here's a fixture I made 30 years ago, all right? And this uses a Gray Hill a clip that what you do is push the resistor down on there, and it's all set up to be very low resistance and what have you. So this is my test fixture, and these Gray Hill clips are fairly expensive, and I checked the price. They're now about $6.50 each. So you need a pair, so you're talking 13 bucks just to connect. But you can use this for sorting components. 10 stage volt, I didn't even bring in that, but that's 10 resistors in series, and you put 100 volts, and then you have 90, 80, 70, 60, and so forth. All right. And battery testing, that's the one that's I think I need to talk about. All right, next. All right, let's talk about batteries. I have to laugh whenever I read somebody and they say, oh, I take my multimeter and I measure the voltage of this unknown battery. Like, for example, I'm not picking on you, Dave.
Okay.
You left these here, okay?
I did, yes.
They became samples for me.
Okay.
And I tested them, and they're good, by the way. So you don't throw them away, they're good.
Well, you can't.
When you test battery, first of all, this is not a battery.
Sure it is.
Oh boy. We'll get it, we'll get it. This is not a battery, but you're going to call it a battery. And Bob's favorite Duracell battery manufacturer.
Whoa, whoa, whoa. Bob does not like Duracell.
Bob said, yeah. There's a bag I gave you, there's a nice pin in there for you to wear. Because Duracells leak. Duracell makes the batteries for Costco. All right. Now, when you test this, you're going to put your multimeter on there. And let's say the multimeter says, oh, it's reading 1.3 volts. Do you throw it away or do you keep it? Well, it's not shot. It's not, it's not 1.5 like a brand new one would be, right? Or 1.56 volts. It's not 1 volt or below because the typical cutoff, the classical cutoff, is 1 volt. So if you use a 1.5 volt alkaline battery or zinc carbon battery and it gets down to 1 volt, your end of energy is there. The internal resistance increases with age and use. And there's always a series resistor with your cell. This is a cell, not a battery. A battery is 2 or more cells connected. A 9-volt battery is a battery, 2 battery.
It's actually 6 quad A batteries.
What?
A 9-volt battery is 6 internal quad A batteries.
No, it's 6 1.5 volt batteries,
Yeah.
cells inside.
Yeah, but you can cut it open.
Oh yes, and they're stacked this way, and they're stacked this way, and there's flat cells used and round cells, quadruple A cells typically. Okay, so how do we test a battery? Well, you use a battery checker. Now, when I bought this on February 24th, 2007, from Radio Shack, I wanted an analog checker, not a digital, an analog. There are maybe 3 measurements that you make in which an analog meter might be better. The most common one I give is audio sound levels. You've seen on amplifiers and meters where they show the music and the meter goes like this, and it gives you so many decibels, okay? That is better than a digital meter, because if it was a digital meter, the numbers would be just racing numbers and you can't read them and it's meaningless. What's the difference between a battery checker, battery tester, and the multimeter? The battery checker loads the battery, and under the load, that voltage becomes meaningful. So what I did, this is the sheet that came with it, and they say, okay, we got a button cell, 1.5 volts. The load current for testing is 1 milliamp, and I added this column here. This is a load resistance that when you read the voltage at this value, plus or minus 0.09 volts for the range, that is the go, no-go test. That makes sense. It's not 100% foolproof, but it's far better than just using a multimeter. Why? Because when you test a button cell, you're putting 1.5 kiloohms across the cell. If you check it with your good, AN 8009 multimeter, that is 10 megaohms across that. That's nothing. you're going to measure the open terminal voltage, and it's not going to give you an idea about the cell. So these are the values, and what you do, if let's say you have a favorite cell that you're going to be measuring. You get one of these, not this one, because this is a gold-plated, high quality. It's a dual banana plug, and you have the ability to put connections to here. And what I've done for my demonstration is I've taken, okay, this is I believe it's a carbon film resistor, and this is 1 watt. And I have 2 of them here on here, so I can plug this into my multimeter, plug it, unplug it, and add that resistance. All right, so I'm going to do that now, and so I have a second resistor. Does everybody know what heat shrink tubing is? Sure. Okay. You heat it up and it shrinks, and if it's 1 inch, it shrinks to 1/2 inch. And it holds things together. So I have 2 resistors. This resistor in parallel with the second one, which is connected to the thing here, and I'm going to use this meter to demonstrate. I'm going to put this here, and I'm going to measure the resistance. And here's what I need. We'll use, that's 14.92 ohms on this meter. Now, if I take that parallel meter and I'm going to apply some current to it, I have a transformer that I bought at Goodwill. That was a 99-cent transformer. You can plug that into there. Now what I'm going to do is use this other meter, and that's a DC voltage, and I'm going to take these leads right here. So I have a DC voltage source. It's not highly regulated, and I'm going to turn this meter on. And, okay, yeah, great. There. All right, so I'm going to measure the voltage here. Is that the other end plug? Oh, yeah, I guess it's.
Oh, this is.
Okay, got to plug in the power supply if we're going to see it. Okay, it's on. And we're going to be measuring DC voltage. There we go. That's 9.184 volts. Okay. Now we're going to look at this display over here. Can we get this? There we go. Okay, that remember this is this here, and now I've got this second resistor. Is it over here now? I'm going to apply this 9 volts to that second resistor, and what's going to happen? What's going to do is, let me do this. Can I do this?
Yep. We'll just read it upside down.
Boy, that's light, that's shadow. Where we get the light off? All right, so that's 14.90 volts now. I'm going to apply heat to the resistor connecting next to it, and it's going to warm it up. And notice that the resistance is doing what? It's increasing. So that's a positive temperature coefficient. I'm warming it up. Now NASA uses a touch. If you take a resistor and put it between your fingers and you can keep them there. It feels hot, but it's not, you don't want to do that. That's at a 114 degrees Fahrenheit, I think. All right, the number's in the paper exactly. So resistors may have a positive temperature coefficient or a negative temperature coefficient. This one is negative. It's going down now. Okay. And it's too hot to touch, so I won't do the smoke test. Okay, so I'll disconnect that. So that's the first demonstration I feel I'm going to have to make. And the second demonstration, I'm going to use the big meter also. And I'm going to, this is a little circuit board. And I bought these, and it's really strange. It's cute. You plug it into a
USB-A.
yeah, any USB 5-volt source, and these will glow bright red. But since I don't have any LEDs to show you, I'm going to use this board, and I'm going to clip it onto this, and I'm going to measure millivolts first. No, I'll just show you what I'm doing here. Now notice that voltage is going all around. It's 18 millivolts, 19 millivolts, okay. I'm going to leave that there, and I'm going to get my flashlight right here, and I'm going to shine the flashlight on it. Millivolts, okay. What? Yeah, okay. Why is that overload? Okay, oh, that's too high, okay. Now I'm measuring voltage. I'm bringing the flashlight there, and see how it's getting brighter, how voltage here? Okay. This is actually generating voltage. Now I have another flashlight, which is stronger, and this is also a flashlight I built as a writing project. I designed and made this flashlight because all other flashlights are designed by idiots, right? And the primary reason is they make them round so they roll, and I can set this at square sides. It's a rechargeable battery, so I reduce all the spring contacts, or what have you, and I have a real flashlight. All right. Okay, let's take a look at this voltage here. Look at that. Look at that. Look at that. Okay. Now, if you're going to do this kind of a measurement, you have to have the light normal to the sensor. This has a feature called min-max. All right. Now, it's set at max. So I'm going to come in here, and as I put the light on it, the voltage is going to go up, and look what happens. It's locked in. So it stores the minimum and the maximum voltage. Now let's see what's going to happen. Let's do this so you can better see the screen. All right, I'm going to come in here with the flash. I'm going to give it really a full-blown voltage. Oh, okay. There we go. 0.860 volts. And I give it different angles here. And if I can get a little bit more voltage, it's going to notice that. Okay, there we go. If I used a regular LED, which I forgot, I can get 1.6 volts out of them. All right? And the reason the min-max feature is so important is that it allows you to make tricky measurements, and you'll get the maximum. You want to know the maximum voltage possible from your LED, and it's going to save it. And so it's a very nice function. But my poor little 8009 doesn't have that. You can't have everything for a $25 or less, depending on where you buy it. All right. And I discovered there's two faults to this meter. As wonderful as I love it, and I praise it to death, The one major flaw in the design is that it's two AAA cells for power, and that has a power bus throughout the circuit board, and that's noisy. So you can add capacitors across that bus, and all of a sudden now, instead of taking 3-4 seconds, and it settles down to the value, and it goes, and it's done almost instantaneously. So cleaning up the noise on that bus, there's one guy who did the best job of describing it. You can find it. The information is all in my paper. I found one other weakness, and that is recently, if I take, I have some test leads. Where's the test leads? No, here we go. Let me get these. When the design of this banana plug is that you put in the, this is a brand new third-party set of test leads, and so they have these on here. There we go. And over here. Now the design of this is that you have a normal banana plug like this, all right, and you plug it in. Well, this one, the banana plug, is surrounded by this plastic sleeve. So when you plug it in to an 8009, you know. Okay, can we? Okay, but if we turn that overhead light, anyway.
There we go.
Good.
Yeah.
Okay, so when this gets plugged in, see that circle around this there? It's mechanically supported. If you take a plain banana plug, it wobbles because it's not designed for that. So that's a minor thing in terms of the, you know, the instrument.
It's also a safety thing because it's providing insulation.
Oh, yes. Now, okay, the professional reviewers on the internet will praise this machine. Now, I answered a question on Quora, and some guy came back, oh, you're just a shill for that Chinese company. Boy, did he get a piece of my mind. The professional reviewers will, you know, they extol the praises, but you can't say that it's all praiseful. You got to find at least one negative, right? I mean, isn't that the law of reviews? And so what they're going to complain about, and they never give any basis for that complaint, and I'm looking for my glasses. Here we go. No? Yeah. Getting old as a pit. They have, these multimeters have a rating that is a category rating. So they say that this instrument is rated 600 volts Cat 3, you can look up this, or it's 1,000 volts Cat 2. And they say, without any backup, without any, a lot of these reviewers are very good. They have the right instrumentation, they describe it correctly, but they always say, I wouldn't use it on any high voltages, which is nonsense as far as I'm concerned. Okay, I'm not saying that the cat is right or wrong. I don't have the ability to test that, and I had never tested that. You end up distorting the meter when you do, and I don't want to do that, even though I have, on this one I have 7 of these, you know. So, oh, Bob is gone, so I guess I'm, how's the time? What's the time?
You've got 2 more minutes.
Oh, I have 2 more minutes. All right, okay, let's do one more. How can I do this? Okay, I'll use it. Oh, here it is right here. Oh, I already demonstrated the light sensitivity of this. Now, if I were to go to Jim Johnson over there and say, Jim, I want you to test this LED, how are you going to do it, Jim?
She's a digital multimeter that has a diode test.
Correct, yes. And almost all medium range multimeters have you know, each of these 1, 2, 3, 4, 5, 6, 7 positions, I guess you could say those are 7 functions. Now, like our calculators, we have shift keys. Over here, for example, this is the resistance. And I'll use the camera for that purpose. We have on here a yellow position, so we can see it on the display here. It's
select hold.
It says ohms. All right, overload, and then I can select this, and now that should change. Okay, there's ohms, and I select this again, and so what Jim is saying that most multimeters have a diode test function, and if you plug in an LED and it's forward biased, does everybody know what a bias, forward and reverse bias means? Who does not? Britisher friend, counter, please record. He's got it. By golly, you Brits are good. And so if you forward bias it, it's going to glow. And that's obvious. It's an LED. It gives light. It's good. I would use a dedicated meter like this one here. Now I don't have an LED to plug in, and I have a writing project describing this. Now I bought this 30 years ago.
What is that?
Huh?
What is that?
Oh, this is an LED tester.
Oh, okay.
Okay, and let me comment on that, and then I'll be good for time. Okay. Can we go down? Let's go down. Yeah, there we go. There.
Yes.
Okay, you see across the top. Can we go even further down?
Yeah.
Yeah. There we go. See this? It's got a socket, a row of sockets, and the first socket is 2. That means 2 milliamps. So it's current limiting. Now, let me jump into that. How many people do not know the difference between a current operated device and a voltage operated device? Oh, really? Come on, be honest. Be honest.
Sure, I'll bite.
Good. Okay, you got the count. Okay, let's, everything, give me 2 more. I'm going to take 2 more. If you plug something into the wall, it's supposed to be 120 volts. And that is a voltage operated device because the voltage is maintained by your power company. And a plus or minus 5 or 10% over that is not going to radically change the power and the current drawn by the device. Now, current operated devices, it's the opposite. It's not a linear function, and I have a plot there I could show you. Current operated devices are LEDs, fluorescent lamps, and neon lamps. Those are current operated devices. They are driven by an AC plug and a transformer or whatever you need to make those devices work. And a current operated device, say like these little LEDs here are rated at 20 milliamps. You go a half a milliamp either different, and the curve is almost vertical. So the actual voltage at 20 milliamps, you go 20.5 or 21 milliamps, the voltage will change radically. So it's current operated. You must maintain a proper controlled.
That drive was empty.
Huh?
That drive was empty.
Oh, it is. Yes. All right. I can't find the curve, but I have a curve that shows this nicely for all the colors of LEDs: white and red, blue, green, yellow, and infrared, ultraviolet. That shows you the nonlinearity. Any questions before before Bob gets really upset? Richard.
Can I see you test a capacitor with that thing?
What thing? This meter? My favorite meter? Yeah. It has a capacitance scale range, yes. Now the difference between
how low is it accurate? How many How many puffs can it,
Can you go back to my paper?
Yes.
And then we'll capacitance, yeah, okay.
how does it test the capacitance? Is it a time constant thing, or does it have a certain frequency oscillator?
Yes,
It has the oscillator.
yes. Anyway, I have a table of my measured specifications, and it would have.
It's in the flash drive, right?
Yes, yes.
All
That's,
of it is in the flash drive?
oh, yes, yes, everything.
get to it.
Now, if I see, this is the meter I really love, but it's kind of clunky. I love it because it has more ranges. I love it because max min. I love it as bigger display. It's nice. Now, if this has capacitance, I suspect it may have 3 ranges. None of your multimeters will measure picofarads. They start at nanofarads up, usually, you know. Any other questions? Thank you very much. All right.